Hello everyone and welcome at this webinar. I'm Rob from Meulen, and I'm responsible for LUX. With LUX, we distribute a complete package of components for the lighting industry where we provide technical and logistical support. Our customers appreciate this complete range of products from optics to drivers and controls combined with our product knowledge. Normally, we regularly organize a day seminar where we want to share all the knowledge and new products of our partners and suppliers with you. Given the current situation, such events are no longer possible, so we go digital. Today, Patrick van der Meulen, Business Development Manager at Xicato, will present this webinar. Bluetooth Mesh, Now and Then. A fine mix of an introduction of Bluetooth and its core competences and characteristics, and a number of use cases where the technology is already successfully implemented. So now I would like to give the floor or screen to Patrick.
Hi, Rob. Many thanks for this introduction. Good morning, everyone. So this webinar is about Bluetooth wireless control, but hopefully it also offers something a little different. It will include an in-depth look at some use cases, not simply in a neutral academic way, but I'll try to couch them with some context of realized projects. The presentation, initially I will kick off with an introduction to Bluetooth. After that, I'll explore what I consider to be some of the core or fundamental attributes of the system, these being a robust architecture, scalability, and ease of use. I'll also discuss one aspect of security with regards to the controls, but also describe some aspects of central monitoring, central reporting, and central control. I will illustrate each of these using installations that are already completed at Ely Cathedral in Oxford, the Copenhagen Museum in Denmark, and the Wadden Center also in Denmark, but then on the coast. I'll then move on to describe some more detailed functions and features, namely sensor, geography, time-based commands, narrations using light animation sequences, and finally location-aware services. These will be explained during some installations we've done at the Queen Diamond Jubilee Gallery in Westminster Abbey, London, Guerlian store in Paris, and the Chapelle St. Antonin in Toulouse, and finally a travel exhibition by Gary Bunt. So first, an introduction to Bluetooth. Bluetooth is a radio frequency-based protocol, and its has been something of an evolution. Initially used for only audio-type connections, it then developed into a very robust communication solution. As a result, when you buy a new set of headphones, or you get a higher car with a Bluetooth radio, you don't question whether it will work with your phone. It will, because it's based on Bluetooth. However, this audio version of Bluetooth, now rebranded as Bluetooth Classic, has a number of limitations. Firstly, it's a point-to-point topology, so it only supports communication from a hub to one peripheral device at a time. Secondly, it requires a permanent connection, so the central device always needs to be on and located a few meters away from the peripheral. If we switch it off or beyond its signal range, the connection is lost. And thirdly, peripheral devices cannot communicate with each other directly. Everything has to go through a central hub. Bluetooth Low Energy, or BLE, was the next step for Bluetooth. It uses the same radio, but rather than having a permanent connection as in Bluetooth Classic, it sends short messages periodically when there's something to say. This means it doesn't need a permanent connection and uses less energy than Bluetooth Classic. So BLE devices can run for a longer period, for example, also on batteries. It makes it ideal for things that need to transmit data periodically. For example, beacons. They are used to deliver location-based services and wayfinding in retail environments and delivering contextual content in museums and galleries, but also for sensors, providing information regarding occupancy, lux levels, temperature, and humidity, and even fitness devices that can monitor heart rates. The next stage in the Bluetooth progression was Bluetooth Mesh, which is where we find ourselves today. Mesh is a relatively new protocol in terms of Bluetooth. It was only published as a standard in July 2017. It's similar to BLE in that there's no permanent connection, but devices transmit only when there's something to say. But the biggest difference is that it allows devices to relay messages, which means there's no longer a need for a central controller to be present. This many-to-many topology, as it's known, allows messages to spread quickly through the network until they reach their intended destination, whether it be an individual device, a group of devices, or all devices within the network. This Bluetooth mesh has been based on the needs of the commercial lighting industry, namely the ability to achieve interoperability, but also to scale according to building size and lighting requirements, and to provide a level of robustness equivalent to that of a traditional wired system, and of course, ease of use. So with regards to interoperability, which is actually the key topic on this list, the Bluetooth SIG Mesh Committee has defined the complete network stack, including definition of the application layer, which contains the models for dimming, tunable white, and color control, as well as for sensor reporting, timing, scheduling, and scene recall. This means that the lighting designers are totally free to mix different manufacturers in their schemes, knowing that SIG Mesh compliance will mean compatibility across all nodes or devices. On the topic of scale, again, with commercial lighting applications in mind, Bluetooth Mesh allows thousands of devices to be connected together and thousands of groups and scenes to be created, but also facilitates a phased approach to implementation as opposed to requiring a complete install from day one. And as our understanding of intelligent buildings develops, this capacity to expand allows a Bluetooth mesh system to be future-proof, not only in terms of expanding lighting requirements, but also including controls for blinds, shutters, and curtains, but also for air conditioning and fans, and a whole host of other applications associated with the ever-expanding Internet of Things. With respect to Bluetooth, to robustness then, Bluetooth mesh transmits messages throughout the network. So if one node is disabled, the message will still get through. The removal of a central controller means that there's no single point of failure within the control system. A Bluetooth mesh network uses multicast, multipath transmission, so messages can quickly reach all corners of a network with low latency, regardless of where they originate. The small size of Bluetooth packages and the speed at which they travel reduces the risk of collision, and messages can also be repeated to provide further protection in the event that some might get lost along the way. And finally, in this list, ease of use. One huge advantage of Bluetooth is its native uptake in the operating systems of smartphones, tablets, and other handheld devices. It's being propelled forward by the biggest names in technology, such as Apple and Google, and supported by every major operating system, such as iOS, Android, Windows 10, Mac, etc. Its usage on all smartphones and tablets opens up opportunities for using these devices for lighting control with apps similar to the ones everyone is familiar with. The next couple of slides will provide a comparison between Bluetooth and other control systems. Then, rather than do this in a general way, I've taken a representative wired and wireless system, these being DALI, which I'm sure most of you are aware of, and Zigbee, which is another wireless controls protocol, but might be not that familiar. So I can give some actual figures as part of this comparison. Time won't permit us to go through everything shown here in great detail. And actually, this topic could be easily a webinar on its own, but we just look at some headline comparisons. First, there's the obvious difference, of course, the control wiring. Put it simply, there's none with Bluetooth or Zigbee, which brings savings in terms of copper, but also installation time. It also makes wireless the perfect solution for listed or heritage buildings, where it's not allowed to drill holes or route channels. So if we look at the 3 points that we discussed before, interoperability is the key one on this list. Once again, the SIG Mesh Committee defined the complete network stack. Lighting designers are totally free to mix different manufacturers' equipment in their schemes, knowing that SIG Mesh compliance will mean compatibility. The application layer for DALI is not standardized, and with Zigbee, the full stack is defined, but in a way that different brands can comply and still not be compatible. Effectively, these represent proprietary implementations, where not everyone is able to take part, and you're essentially tied into a single system. When we look at scalability, with DALI, only 64 devices can be connected into a single bus. Of course, you can have multiple buses, but then a control system is required to link these together, which can be both complex and expensive. With Bluetooth and Zigbee, 10,000s of nodes per network are possible. And the third topic was robustness. A DALI installation is very complex. Many devices can fail. DALI masters, higher level controllers, signal amplifiers, power supplies, etc. If one of these fail, then it could be that the whole system won't operate. This is also true in some extent to Zigbee, which has group coordinators and the hub. With our Bluetooth solution and the fully distributed intelligence design, if any one node fails in itself is an issue, but it doesn't affect the installation. There's no single point of failure. Next step, we take a quick look at some different network speeds. Compare the 1.2 kilobyte per second polling bus of a DALI system, 250 kilobyte per second for Zigbee, and 1 megabyte per second for Bluetooth broadcast. But even more important in terms of speed is that with centralized control, there are multiple lines of communication between the sensor being triggered, for example, and the light responding. This is because the devices cannot talk to each other. They can only reply to a command from a DALI controller. This DALI controller must poll each device sequentially to ask if it has anything to say, then sends out a consequent command to each relevant device in turn. With Bluetooth, each light point hears input directly from a sensor and switches and makes an independent decision about its reaction. With Zigbee, this is true, but to a lesser extent, as groups of nodes are coordinated, but commands must still come from a central hub. The next item in our table is security. I would say this topic also fits under the umbrella of robustness, of course. But to hack a DALI system, you need to get access to the wires or hack the local area network. With Bluetooth and Zigbee, you need to get access to the wireless signal, then decrypt a 128-bit AES network key, something which has never been achieved through a brute force attack, only by guessing or getting access to IDs and passwords. We've already discussed ease of use being helped by the uptake of Bluetooth on smartphones and tablets. Pretty much everyone can become involved. And this is becoming more and more widely accepted practice, especially when discussing circadian lighting with an individual work environment. This ubiquitous availability is only true for Bluetooth. And finally, I brief on additional functions which are possible with Bluetooth, but not possible at all with DALI. Bluetooth-based lighting controls can also incorporate many other control elements. Think in terms of sharing sensors or controllers with other building functions to create an integrated building management system. Think about heating, ventilation, and air conditioning, security, like doors and windows, space utilization management, and other analytics, asset tracking, and precise indoor tracking. Some of these, if you like, IoT functions are possible with Zigbee, particularly in the field of home automation, and there are over 500 members of the Zigbee Alliance. However, it cannot be compared with the ever-increasing proliferation of Bluetooth devices and users. So to wrap up this very quick comparison of control summary, when comparing Bluetooth to DALI, Bluetooth is faster. It is native to mobile devices, fully interoperable, more scalable, supports additional functions, and requires no control-specific wiring between nodes. When comparing Bluetooth to Zigbee, Bluetooth is faster, native to mobile devices, fully interoperable, and more robust, more secure. Bluetooth is fast establishing itself as the communication method of choice for wireless lighting control systems, and fast becoming a major competitor to the more traditional DALI controls. Now we move on to look at some more Bluetooth control fundamentals. Every time we compare back to the original scope of this presentation. So first, I'm going to discuss scalability and robustness. And in this project, we refer to the Christchurch Cathedral installation. So the first slide shows an outline of the plan of the site, where there's a new lighting system to be installed in 2 phases in order to allow the building to remain open for tourists and worship whilst work is in progress. A master plan with different phases was made by the lighting designer with this in mind, and also in line with the budget availability. So a control solution which was able to scale as the refurbishment work progressed was essential. In this example, you will see that to make a robust mesh in a situation where component placing was far from ideal posed further issues. And we will show how these issues were solved to illustrate Bluetooth in practice in the context of these fundamentals. In the main, as you can see from the area shown with the blue ellipses, The first phase was to cover the entrance area, nave and north transept, but also notice the 4 spotlights in the Latin chapel on the top right of the plan. These are already remote from the main locations. Straight away, the topic of scalability and indeed flexibility is evident. Not only is there a phase implementation, but the areas under refurbishment during each phase are not essentially adjacent to one or the other. So having said this, look at the switch positions. These are shown by the green triangles. One at the main entrance and a second in the AV control booth. Distances between the nearest switch and the more extreme lighting nodes locations are in excess of 40 meters and without direct line of sight. Any radio signal will therefore be decreased due to the attenuation caused by walls and other barriers. The usual approach here would be to configure a series of lighting nodes and possible BLE switches as repeaters to create our mesh network. These repeaters receive commands from the switch panel and pass them on around the network, thereby extending the network reach. Obviously, this relies on each node being within the signal range of its neighbor, and best practice is to configure multiple repeaters in each such that there is no single point of failure. However, this needs to be balanced against having too many repeaters, which can cause an overload of messages entering the system. A rule of thumb, up to 200 messages per second can be sent within a given space before the network performance begins to suffer. Unfortunately, however, we found out, being on site at the installation, that some of the Bluetooth drivers for the north transept lighting had to be sited remotely in a cupboard on a mezzanine level behind a stone balustrade. It's the red ellipse shown here. There was in fact no Bluetooth communication between this location and the main body of lighting, and any chance of achieving connectivity to the lights in Latin Chapel also had to be removed. The solution here was to deploy relay nodes to effectively bridge the gaps, so tackling scalability and robustness problems. Relay nodes are, as the name suggests, a simple Bluetooth node with a single purpose to relay messages. They are not integrated within the LED drivers or bridges, etc. Firstly, we had a permanent installation to provide a staging point for communication to the BLE drivers on the mezzanine level, located within a plastic housing on the left-hand side here. Because this is a permanent integral part of the infrastructure, there are 2 relay nodes within the housing, again to eliminate a single point of failure. The second relay node extends the BLE network to reach the Latin Chapel with the 4 lights and is disguised to look as a part of the ornamental fencing. The simple addition of these units allowed us to control all of the lighting deployed as part of phase 1 from both control panels with no latency issues. This first phase lighting control system has been in use for the best part of 12 months, and phase 2 installation and commissioning had just been completed. The second phase, new lighting, has been seamlessly integrated into the existing control system. As part of the second phase, additional repeater nodes have been configured, which will turn into the extent of the mesh, allowed the removal of the temporary nodes that we showed before. Staying within the Christchurch project, we will now have a look at how rather complicated implementation can be first made simple for those with the most basic requirements of scene recall. Second, provide a more granular real-time control via an app or on a phone or a tablet. Today, at the Christchurch Cathedral, there are 150 nodes, being a mix of single and multi-channel devices. Lighting nodes are assigned between 45 groups based upon location and function. For example, all nave lighting, that's a location, or all nave lectern lighting, which is a function. In total, 14 scenes, including cleaning, which sets all the lights at full, off when the building is empty each evening, and 12 surface-specific scenes designed to provide lighting effects according to seasons and celebrations. There's also a requirement for raise and lower functions to be applied across all individual luminaires, groups of luminaires, and all lighting. There are also 2 different user groups: the cathedral manager and the majority of the clergy, who possesses technical know-how. In fact, in this case, the cathedral manager has a background in theater, sound, and lighting. But these two groups of people are familiar with phone and tablet apps and want to utilize the lighting to maximum effect, possibly in real time. And secondly, the volunteer guides and helpers who are less technical and ask for more simpler control, like light switches in the home, for example. So how can we cater for both? If we may start with the last group, those requiring the simple level of control, but still wanting full control over selection of all pre-programmed scenes. We deployed easy-to-use push buttons, panels to provide control from two locations, as I mentioned previously, one being in the main entrance and the other at the control booth, where sound equipment and the original lighting system was located. Each panel consists of 16 buttons. Button 1 brings all lights up to 100% for cleaning and maintenance. Button 2 to 13 recall pre-programmed scenes, as I described earlier. Button 0 turns all the lights off, and with the up-down arrows, you can raise and lower light levels across all luminaires. On the push button, an LED illuminates when the button is pressed to identify which scene is currently active. The LED illumination is tracked and applied to both panels. A written list of button numbers and associated scenes was made available for reference or to act as a reminder. For the cathedral manager and clergy, who will use the system daily, an iOS app provides the more granular real-time level of controls which they require. The app allows selection of a single luminaire, which can be turned on and off, or have its intensity raised and lower. Selection of any of the 45 predefined groups, which can again be turned on, off, raised and lowered. And all lights can be controlled in the same manner via the selection of a broadcast group. And any of the previously described pre-programmed scenes may also be recalled. In terms of the user interface, icons for lights, groups, and scenes are shown at the bottom of the screen. The lights page shown here as a list of all luminaires. Each can be turned off by tapping the button to the right. Selecting an individual luminaire will drill down a display slider, which can be used to raise and lower the light intensity of that single luminaire. By selecting the group icon, it takes you to the groups page, which will display a group of pre-configured groups. Again, the button to the right of the group name can be used to turn on and off all the lights within the group. By selecting a group, it will drill down a list and show all the lights within it, and will display a slider, which can be used to raise and lower intensities within a given group. By selecting the scenes icon, it will display a list of pre-configured scenes, each of which can be recalled by a tap in the same way the push buttons were used as we described earlier. And here we have a result of the final lighting. Next, an example of utilizing secure networking. I'll refer to an installation at the Copenhagen Museum. If we start with the exhibition lighting plan for one of the 3 floors, all exhibition luminaires, 300 in total, are under Bluetooth control. There's also some designated emergency lighting installed on each floor, represented here by the red circles, superimposed over the decorative lighting plan. The challenge here is to ensure that the access to the different lighting types is available only to those who warrant it. Curators require full control of exhibition lighting only, whilst the building management team requires full control of both exhibition and emergency lighting systems. So the solution here is to deploy 2 secure networks and define access to each within the control panel side file and within the Bluetooth app. The curator side file has access to exhibition lighting network only. The building management side file has access to both exhibition lighting and emergency lighting networks. These secure networks are then mapped onto Bluetooth devices for the respective departments. So this is a screenshot of the control panel. So within the Bluetooth control panel, the setup was as follows. First, we created a curator side file. And within this site, we then defined a secure network, also called Curator, into which all exhibition lighting was placed and therefore visible by those using the site file. We have then a building management site file. In here, we have two secure networks defined. First of all, the Curator network, as previously discussed, but also the additional manager network into which the emergency lighting was placed. The building management team has access to both sets of the lighting. Within the Bluetooth app, of course, on the Curator devices, we only configure the single network for the Curator, which has access only to the exhibition lighting. Whilst on devices used by the building management team, we added the second network as well, allowing them to have control over all lights, and thus able to secure access to the system based on the user's requirements. And look here at the result. So we are, of course, limited to two user groups, requiring different access to the different levels. But of course, this can be extended to multiple networks, so we can have individual control over the local settings. We now move on to centralized monitoring and reporting and control. For this, I'll refer to an implementation at the Wadden Sea Center in Ribe, Denmark. It's a UNESCO heritage site and incorporates a museum and a learning center. In terms of monitoring and reporting, details such as temperature, input voltage, intensity, and lux hours are recorded by a series of BLE to IP gateways, which you can see on the top right box of the screen. These gateways are connected to the building's Ethernet network along with the building management system. The information related to the lighting performance is captured and reported into the building management system via the gateway's application programmer interface. The gateway also provides remote access to the lighting control system. This is what the connectivity looks like. 148 lighting nodes are installed within teamed areas, communicate with 6 gateways via BLE, as mentioned previously. These gateways record information relating to performance, which is received by the BMS, also network connected. And with regards to the centralized control, the eviction lighting is integrated into a DMX DADI control system from Meulen, which again is network connected. Pre-programmed scenes for exhibition open. The lighting designer defined all the intensities for each light. Another scene called closed. All the lights are dimmed to 0% intensity, and cleaning. All lights raised to 100% intensity, which are triggered through the Meulen's user interface located in the reception area, again using the API calls. Additional scenes have also been programmed to allow control over individual rooms, also available from the same user interface. This installation really demonstrates how monitoring, reporting, and control functions within exhibition lighting, DMX and video content can be brought together, building on our previous theme of robustness and ease of use, and incorporating centralized control and systems integration from a single, simple-to-use, menu-driven touchscreen drive. So now, move from the fundamentals over to features. The issue we tackle here firstly concerns the ability to subtle orchestrate the direction of different lighting nodes triggered by one sensor trigger input, though also the input could be time-based or another trigger. The beauty in this respect of a mesh system is that there's no latency effect or complication of one centralized control sending out commands. Here, each node triggers within milliseconds other nodes, which react as they have been programmed to do so. The second issue concerning programming of hierarchy of commands coming from different sensor types, which takes precedent over which. Take, for example, LUX and movement detection. There could be other layers too, for example, overlaying a time schedule or end-user switching via the state machine. For my example, I've used a museum within the Triforium Gallery of Westminster Abbey called the Queen's Diamond and Jubilee Gallery, which was opened in June 2018. The brief was that energy savings would be achieved by only having lighting on when there's someone present in a given bay. The museum is set out in a number of bays as you walk around the gallery. On the left plan, you can see more or less that there is a sensor position in each bay, described by the circles. The idea, and I hope this inset makes this clear, is that a visitor moves, let's say, into bay 13, where the lighting is already on. Then the sensor there, labeled bay 13 sensor, triggers the lighting in bay 14 to slowly rise over a period of 5 seconds. This means the visitor never feels in a cocoon of light. There's light in the periphery, but also that there is no abrupt changes. So we have a very subtle orchestrated energy savings via presence detection. If there's no movement detected after 5 minutes, then the lighting fades down. There's also LUX sensing. Artificial lighting is dimmed or even switched off if there's enough natural light to retain the designed illumination level, let's say 50 lux. With the hierarchy of commands, presence detection comes first. If there's no one present, the lighting is off. But when it's on, it's tempered by daylight ingress. In the picture, you see the lighting designer, Peter Foreman from DHA Designs, measuring the lux levels on an exhibit. In the next slide, I will show you a simplified screenshot of a control panel showing how this is done. But what I won't do is go into a third possibility of the sensor command, and this is to measure the lux hours that has actually been on the object, on the exhibit, because this can be measured and triggered as well. And as a reference, in the time that it's been opened, actually they found out that there's less lux hours on the exhibit, so therefore they have increased the general lighting of the total installation. So here you can see a simplified programming of the previous use case. Upon switch on, there's no movement. The lighting is in state 0. In this state, it is looking out for a motion event or a command from a light controller. If there's a motion event, then the lighting will track 750 lux on the sensor, meaning it will dim up or down to get this fixture depending upon the amount of incoming daylight. This is state 1. State 1 then looks out for a motion timeout or a light control event, both of which override it. State 2 is the light control command. Both state 1 and state 2 look out for a motion timeout. This overrides all. Now we move to the topic of scene recalled by points in time. We will expand this theme by again integrating these time triggers with other triggers and also making a revolving scene loop, creating a narration. We'll use 2 French testimonials to explain these processes. Firstly, the Guerlian store in Paris, and secondly, the Gauvin de Jacobin in Toulouse. Starting with the Guerlian store. Here is the time-based lighting schedule designed by the lighting designer, in this case Voyant Foire. From 8 o'clock in the morning till 9:30, we recall scene 1, cleaning. All lights are on at 100%. At 9:30, the shop opens and scene 2 will start. This will continue until 7:30 p.m. The shop open scene has daylight links for energy saving and comfort. From 7:30 to 12 p.m., scene 3. This is the evening scene. Much lower light levels, but still the store has a presence in the 24-hour life of Paris. From 12 to 2, evening scene reduced by 25% every 30 minutes. This is a subtle reducing of light. This linked to fewer people on the streets and decreasing need for lighting along with reducing energy consumption. From 2 a.m. till 8 a.m., scene 4, nighttime deliveries. The lighting is off, but some lighting is triggered by a PIR when delivery arrives. So let's have a look at some of the programming. This might at first glance appear complex, but trust me, it isn't. And there's the added advantage that designers only need to tell us what they want and we can take care of the rest. The first scene that you see here on the control panel is a recall during the time period T0, which you can see is from 8 a.m. to 9:30 a.m. on weekdays and Saturdays. During this period, the command is to recall scene 1, which is our cleaning scene. And this is what it looks like. You can see early in the morning, light outside, and the lighting internally is on fully as the cleaning is being carried out. Now we come to the next time period, which is T1, for the shop open period from 9:30 until 7:30. So now the command is to recall a shop open scene, but also see that the command changes as to whether a photo cell near the window, you see it in the picture, is reading more or less than 300 lux. And again, this is what it looks like. The pictures were in fact taken simultaneously. In reality, even when there are different natural light levels, the difference would be even more indistinguishable. Our next time period shown here is T2, between the hours of 7:30 and 12, during which lighting is still present, but more subdued, as shown in the image in the lower right. Then we move into the early morning time period from 12 p.m., where we can see the light's intensity drops by 25% each 30 seconds, which is achieved by recalling additional lower intensity scenes until finally fading to zero over a period of 60 seconds. Once we are into the light out time zone, we then switch to a sensor input and recall the delivery scene when the motion is detected. At this point, some light come up and remain on until 50 minutes after the last motion detection event, thereby ensuring the lights remain only on until after people have left the shop. And finally, the last piece of this control scenario, we add a manual control override, which can be seen here. So on this example, we've input triggers provided initially by time events, followed by time events supplemented by a LUX sensor during the day, then moving on to time events supplemented by motion sensors during the night. And finally, an override switch to pass control back to the shop staff at any time should they require it, such as Sundays or holidays. Now, moving to the theme of narratives. Chapelle St. Antonin at the Couvent de Jacobin in Toulouse has been some of the finest surviving late Gothic frescoes in France. The lighting brief by Stephen Kenneth Brooks, including creating dynamic highlighting of the different lighting fresco paintings in a loop, such that the story of St. Antonin's life could be told. No new cabling was allowed within the site, and Bluetooth-enabled lighting equipment had to be concealed in freestanding, custom-designed furniture, which provides visual balance and acts as an invitation to visitors to sit and view the frescoed ceiling and upper walls as a whole alongside the dynamic sequence. Here you see the lighting designer's vision of a smooth sequencing of the lights between different targets on the ceiling. And here you can see a sample of the programming to bring this about. Simply put by a series of loops and triggers are programmed into each individual luminaire to recall a succession of predefined scenes, thereby creating the overall animated sequence. This operation is integrated with a portable energy harvesting switch, which is used to start the animation in the morning, stop it in the evening, and during guide-led tours, the sequence can be paused and resumed while specific features are highlighted and discussed. And now move over to a small video which has a quick animation of what has been achieved. Okay, let's come to the last part of this presentation, location-aware services. So this is a non-lighting use of our Bluetooth-enabled luminaires, and this is based upon locations. So we all know the global positioning system, so-called GPS, and the application it enables, such as car navigation and speeding the delivery of emergency services. But the signal from the GPS satellites doesn't enter buildings, and even if it did, it wouldn't be accurate enough for indoor use. For indoor applications, you would like to be able to discover which floor of a building you are on. And if you are in a store or a museum, you would like to know which object you are close to within an accuracy of a meter or so, in order that you can provide the user with more information about the objects they're close to. Once again, this is a feature you can use Bluetooth for. When a broadcast signal or a beacon is received by a dedicated beacon app, Then it triggers the app operating system to display something, location, some specific information to the location. Most beacons used today are retrofit and battery operated. And as a considerable battery power is needed, otherwise their replacement would be a constant obstacle, the devices have to be quite big and, dare I say, unattractive. This way of working becomes redundant if you have powered beacons overhead or in cabinets where there are BLE drivers, basically where you might already have a light. The example I will use here is a usage in the Ely Cathedral tour app. There are exhibitions. This exhibition is entitled Bert, His Dog, Our God, and is shown in several English cathedrals throughout 2020 and will now extend to 2021. The app is a guide that accompanies the exhibition and provides information about the artworks and interview with the artist and information about the venues and dates. The image here show Bluetooth lighting installed on each plinth to illuminate the artwork. The same Bluetooth nodes are also programmed to trigger an app response when someone with a smartphone and of course the app downloaded on it passes within a given distance. The distance can be adjusted by altering the measured radio signal strength. There are 3 beacon types which may be configured into each Bluetooth node. Eddystone, which broadcasts a URL or website address. A mobile device app, which is configured to recognize Eddystone, would respond by prompting the user to go to that URL in a web browser. The iBeacon and AltBeacon, which are very similar, broadcast a combination of identifiers. An app which has been programmed to look for these specific combinations or identifier will then carry out an action when it detects them. In this particular case, an app has been designed which detects iBeacons. It will scan in the background for a particular value, known as a Universal Unique Identifier, or UUID, and then take action when it detects any beacon using that specific UUID. In the case of the Gary Bunt app, all the Bluetooth modules use the same UUID, and groups of between 6 and 8 nodes issue the same instruction. When the app detects beacon, it registers the instruction and then automatically jumps to a page in the app that lists the corresponding group of paintings. Once the initial provisioning has been carried out, there's no need to revisit. When the exhibition moves venues, it is simply disassembled and packed away, then unpacked and reassembled at a new location. Lighting levels and beacons information both reside permanently within the Bluetooth node, though lighting levels can be adjusted again via an app if required, and the relevant information is delivered to the visitor's device. They move around the exhibition wherever it resides. That concludes the webinar for today. Thank you again to everyone for attending. I really do hope you found it very useful. And now I'll be happy to take any questions, or we can check the chat box. I see a question regarding thicker walls. As I described in the Christchurch Cathedral, we can make use of repeaters. So even though there's no lighting around, you can still use repeater nodes to move around thicker walls. Next question I see is about integration with other BMS and control systems. As I described, Xicato has a gateway which uses an open API. Through this open API, already several integrations has been made through DMX, like through the Faro system or Vantage, but also Crestron and other control systems are possible. The link will be through the network. At the moment, the next question is, can presets be changed in the iOS app? Today, all the settings are done through the control panel. Presets cannot be changed yet. Of course, you can change the value of the lighting, but this cannot be stored into the lights at this present time. But we're working on an upgrade of the app that will make this possible. Next question, I see offices with metal ceilings. So basically, usually the lighting is below the ceiling, and this will make the communication still possible. Please know that also many luminaires are into metal fixtures as well. But at the end, the antenna is on the front side of the luminaire, so you will always have a mean of communication. I see a question. There were many difficulties when many Bluetooth devices are kept in a small space, lights, sensors, and cell phones. At the end, this is all comes to networking. If you keep the mesh network as low as possible, then you will never see any bouncing. I would even be more worried for people in a space because people are mainly made out of because it's out of water, and water is actually absorbing the signal. So I don't see any problems with multiple Bluetooth devices in the space, but more even the people. Then I see a question. To program, you could have issues to find your nodes. I don't understand this problem. So when you're on site, basically each device is broadcasting itself, and with the app you will detect everything that's in the space. Of course, assuming they have not been secured, because if they have been secured, of course, then you won't be able to have access to them. Another question, can you work with RGB, RGBW, or strictly white? Yes, this is possible, and this will depend on the driver or dimmer. But there are dimmers on the market available that actually allow you to control RGB or RGBW, or only white. See a question, are there possibilities for people counting? Yes, this is possible. There are two ways. Of course, you will have, you can use the sensor using the PIR, but of course the challenge there is that you don't double count. A better way is actually using the beacons and an app, because then you will have through the MAC address of the phones, you will have unique people. Another question, do you need your backup file to program, or can you read from the Bluetooth mesh system? Basically, like I described, everything is local, so you actually don't need a backup. Everything you will get from the nodes from the system itself. Of course, if you think about scenes and groups, all this information is stored into the lights, into the nodes. So this requires some form of administration that you actually can keep this data, because this won't be available offline for the moment. Then there's a question, fully compatible. I don't know if that's a question or a remark. It's fully compatible BMS with IP. I just can rephrase this, is that through the open API, it's compatible with many of the building management systems. And as we are working on it today, many building management systems will have the API integrated into their system. So there's no need for to write the code yourselves. Yes, the app can be branded. It means that we have the full API available to anybody, which you can use, and then you can make your own graphical user interface. But the code is available. Okay, thank you all for attending.
Thank you, Patrick. Thank you very much for this very interesting presentation. I think we learned a lot today. If anyone has more questions, Patrick and our team from LUX are always open to answer to your questions. Thank you very much. Bye-bye.